I mean, when you give a lecture, usually in a classroom, you have a lot of time and you give all the details, and it should be understandable from step to step. And when you give a survey talk, it's more that you give a statement and then you just sketch the proof, right? So you leave out details and just want to give the idea. And sometimes even for the statement, you simplify it a bit in order to maybe save some time, or just to give the idea of what's going on. And the details are left for the reader in the journal. So for this lecture here, for these 8 lectures, I had to balance a bit. So the details and also the survey character. And I have the impression that last time I was more in the survey character when sketching this Tanaka-Krein duality, but you wanted to see some more details, and then we came to the details, and then in the end there was a bit confusion. So this is why right now I will once again tell you a little bit about this Tanaka-Krein thing, how this is related with easy quantum groups, because I don't want that you leave you alone with the impression that easy quantum groups is just related very vaguely via Tanaka-Krein. Okay, so I will try to make this a bit more precise today, and then we proceed with the easy quantum groups and see what else can be done. Okay, so this is why I have some extra chapter maybe. So from Tanaka-Krein to easy quantum groups. So last time I defined what is a category of partitions. So we start with that. Okay, so recall that this consists of some subsets CKL of partitions PKL, where K and L are natural numbers, including the 0. You have K upper points, L lower points. You can connect them by strings. And we take some subsets of these things. And this forms a category of partitions if it's closed under the tensor product, the composition, and the involution. And if you have that this identity partition and the pair partition, they are in C. Okay, so this was the category of partitions. We start with that. Then we associated a map TP. Okay, so here a basis vector was mapped to the sum over all possible choices of basis vectors here, but we only pick those where the indices and those indices in the target space are connected via this partition P. So last time I defined this, and then we saw that the span of all these TP this is closed under tensor product, composition, and involution, since we have something like that if you take the tensor product of 2 partitions, this yields the tensor product of the associated maps, and same for composition, involution, and so on. Okay, since we have something like this, we know that this is closed under these operations. And let me now define a monoidal category associated to this, from which we get a quantum group. Okay, so this monoidal category, if you really want to see exact the details, like what Vodonovich did, he did it like that. So we define R. It consists of some index set R. Then we have some Hilbert spaces HR. Then we have some morphisms. We have some operation and we have some element f. And in our case, what shall we do? We take this index set, just the natural numbers. The associated Hilbert spaces will be HR of this form. The morphisms will be our TP. And the binary operation is addition, and f is 1. Okay, so this is for a chosen n. So hence we can say R depends on this natural number n that we've chosen here. It depends on the category of partitions.
F is 1.
Yes, f is 1, yeah. It depends on the category of partitions here, and it depends on the way we associated a map TP to P. Okay, so these are the things, the parameters that come into play here, and this is a monoidal a concrete monoidal W star category. So I don't want to write down all the properties. I did it last time, but there was, for instance, if you take two morphisms, then their tensor product is again in here. Okay. So let us just check the flavor of this. Okay, so T1 is a morphism from R1 to S1. This means my T1 somehow goes from HR1 to HS1. So this means I have this Hilbert space to the power of R1 and this Hilbert space with the power of S1, and my T1 is a morphism from here. I get another one from here, and then it goes from R1, R2, which is by definition R1 plus R2. Okay, so if I take here R1 plus R2, I get this Hilbert space tensor R1, tensor the Hilbert space with R2. Okay, so this is true, right? So this tensor product, and then we also have some other properties, with something like composition, involution, existence of an identity, and some other things. Okay, so I wrote down this list last time. So we can check that this is really a monoidal category fulfilling all these properties. Now there's a notion of a conjugate. So last time also I was a bit vague with the conjugate, so let me tell you what the conjugate is. So we say R bar is conjugate of R if there exists a J going from HR to HR bar, antilinear invertible map, such that Tj is a morphism from 1 to R bar, and Tj bar is a morphism from R bar R to 1, where Tj is this map, giving just by mapping 1 to the sum over all EI, tensor J of EI. Yeah. Okay, so this depends on the dimension of this HR, which in our case, of course, is here, this one. Okay, and Tj can also be defined, so let me omit this. Okay, in our case, we have f equals f bar, since j of Cn to Cn, which is just given by this map, this yields T1 equals EI tensor EI. Okay, so my J is just the identity, okay, so with this complex conjugation. So this is my T, and what is this? Well, this is exactly, if under this map, P to TP, so this TP, if I take this partition, then this yields exactly this one, right? Because what does it mean? So here, this is my basis vector for C. And in the target space, here I have 2 dimensions. And it sums over all possible choices of the indices such that those indices are the same, right? So I sum over all EI tensor EI. So this is in my morphism space from 1 to f bar, which in our case, okay, this is a bit strange. Here I use the sum, so this one here is 0. Okay. Okay, so here I have f plus f bar. This is 2, and this 1 is the 0. So this is in my morphism space. Okay, so since this is a morphism, by definition, we see that we have f equals f bar in our case. Okay, so now the next step is we need a generating set, namely, in order to apply Voronovich's theorem, we have to say that the set consisting of f and f bar generates the whole category, and the precise definition for this is the following. So this generates R if for all S and R there exist morphisms Bk from some product of elements from Q to S such that, okay, finite choice, such that K, Bk star equals the identity. Okay, so this is the definition for the fact that Q generates R. So this is a bit strange if you see it like this, but if you think that at some point you would like to have a completion of R, so going to subrepresentations, here's a description for subrepresentations. Okay, so this means in this sense Q generates the completion of R if you also allow further properties than only these one, namely the relations for a complete monoidal category. Okay, this is the idea why this is a good definition, but the precise definition is like this. Okay, and in our case we have this F generates R since, okay, F products of F, this is just S, and we can just take for S in R, we take Bk equals the identity. Okay, and this is a morphism. So this is in our morphisms when you define it like this, because last time I also said that if we take this identity partition, then this T associated to this is the identity map. Because it should map an element from here to an element here if and only if these indices coincide. So it's just the identity map. So this partition gives rise to identity maps here. Tensor products of these partitions give rise to this for any power here. So we always have these identities in here. And we just take bk as this identity and we get the whole thing is generated. Okay, and now, due to Voronovich, due to theorem 3.15, which is in Voronovich, Tanaka, Krein paper, this is theorem 1.3, there is a compact matrix quantum group G equals AU such that first AUR is a model of R with UF equals U. What does it mean that it is a model? This means that these UR are unitaries in BHR tensor A. And we have URS, so with this binary operation we have in our monoidal category, we have that this can be written as a tensor product, and we have intertwining condition. Okay, we have such an intertwining condition for all R and S and R, and T a morphism. So in our case, this just amounts to saying that we have U tensor K, TP equals TP U tensor L for all P and C L K. Okay, so this is the intertwining condition. In our case, these maps T from these morphisms, so the way we defined our R means that these morphisms are these TP. Okay, so this is here this T in our case, this is the TP, and this U to the R, this is just U to the 1 plus 1 plus 1 plus 1 R times, and this can be written as the tensor product. Okay, so this is the translation to our case. And also we have U equals U bar because of F equals F bar. So here I checked F equals F bar. So this in our case this translates to the fact that U equals U.
What was F again?
F is just I define I take any element F, and in our case I just define it as 1. And later when we associate this quantum group, we say that this quantum group gives rise to a model if this U that I have here is exactly this one coming from this F. So this means that abstractly I say this category is generated by some element F, and later in the model this F is interpreted as this unitary U. Yeah, so this is this step from the abstract abstract category to a concrete object, namely the quantum group. You somehow have to interpret the category with some matrices. Okay. So this is one of the assertions of Voronovich's theorem. The second one, it's universal. So it's the smallest C-star algebra. containing the matrix elements of U. And it's universal. That is, whenever we have another model, in this sense that I wrote here, whenever we have another model, then A maps to B. Yes?
What is R bar is conjugate of R? I'm sorry if it's getting mistake. So
Yeah?
yeah. So you take an element R from R.
Yes?
Then you define R bar.
Yes.
How do you define R bar?
So I just say R bar is also an element from R, and it's the conjugate if it satisfies this.
There exists a linear map and that
If there exists,
an antilinear map
yes,
such that
Tj is a morphism from 1 to R bar, where Tj is defined as this.
what is Tj bar?
It's also defined as something, so I didn't want to write it down, but you can also write it down
What
explicitly.
is, they don't satisfy anything. Tj bar should be identical or
They should.
no relation between Tj and Tj bar.
No, there's an explicit definition for this Tj, there's an explicit definition for Tj bar. And if it's a morphism of this form, then you have it. I mean, this Tj bar is given by a scalar product, right? So this Tj bar goes from this space to this space. So you take elements in here, you take the scalar product with respect to the J. Okay.
And you define the universal, what is the quantum group? The quantum group is the C star algebra generated by universal URS, is it?
Yes. So I mean, here I'm just saying I have a quantum group, and it's given by some C-star algebra and generated by some Uij's. It's a compact matrix quantum group, and it should be a model in the sense that to each R I associate UR a unitary such that these equations are fulfilled. So in fact, it comes out from the statement, since A is the smallest C-star algebra containing this matrix elements of U, so it's generated by this Uij, and it is universal in this sense, we see that A in fact is a universal C-star algebra generated by these Uij and these relations.
And Tanaka Grind tells you that such a model exists.
Tanaka Grind tells me if I start with such a model, I will get a quantum group associated to it.
What do you mean by smallest C-star algebra? That is not clear.
Yeah, okay. So it means it's the C-star algebra
Generated by
these Uij.
universal properties there, so I don't understand the smallest.
Yeah. What do I mean by smallest here? Okay, so this U.
A is certainly generated. So A you are getting from this theorem of Voronoi.
Yes.
And you're saying that it is in fact generated by matrix elements of U. That's
Yes,
fine.
yes,
And then you're saying it has the universal property.
yes.
But the smallest one is.
Yeah, the smallest one is a bit strange here, that's true. But this is the wording of Voronoi. But I guess he really just means it's generated by the matrix elements of U. Okay, so this is part A and B. And let me also write down part C. And this is, I guess, the point where there was some confusion last time. Namely, we have C. We have that the representation theory of G is the completion of R. Okay.
There is a compact quantum group A,
Yes.
which is generated by UR, right? Or it's just generated by one single U.
This is just generated by one single U.
Or because the F generates a category.
Yes. Yes, exactly. Yeah, so Volonovich says that if you start with any monoidal category, in our case I wrote down explicitly how this is related to our category of partitions, but in general you just have R, HR, these morphisms, this operation, and some generating F, fulfilling these properties 1 to 7. I just start with something like this, and then I get a quantum group associated to this. This is Volonovich's theorem. Okay? And the fact is, if I now take the completion of this R, so I allow subrepresentations, direct sums, and equivalence classes, then I will get the whole representation theory. But the really nice thing is that if you can think of it in the converse sense. You can say, okay, I want to have a quantum group, so if I just give some representation theory, I get the quantum group. So that's okay. But usually this is pretty complicated, this R bar. But the nice thing is, this is a much simpler object, this R. So for this R, I mean these properties here, they don't look too complicated. So I can write down explicitly, and in our case with these easy quantum groups, I can really label it in a very explicit way. And just if I do some magic completion, I get the whole representation theory. Okay, but this is a much easier approach to a quantum group. You do not have to specify the whole thing, but only this R, and then you take the completion.
Can you leave out the irreducible representation? Can you say?
You mean for general R or for my R?
For your R.
For my R, this is a whole article. It's a whole journal, a whole paper. So I did this together with Amaury Frelon. So you can read the representation theory just from this combinatorics. But
Irreducible representation.
yes, but you really have to work for it. So it's work, because determining the R, that's not so complicated. I just take this category, I just associate this TP, and I do this definition. So this is my R. That's not so complicated. But if I really want to describe this completion, this becomes complicated. Okay, so maybe if I have time next week, I will just speak a little bit about this. But yeah, so what you keep in mind is that the nice thing is you only have to specify the R and not the completion of R in order to get a quantum group.
Can you explicitly compute the Clebsch-Gordon coefficients?
The which one there?
Clebsch-Gordon coefficients?
In this easy quantum group sense, I don't think we wrote something down for this, so I'm not so sure if I can.
Fusion rules are not known.
Yes, yeah, I mean we have fusion rules for if the C is a non-crossing category, we can write down the fusion rules.
Yeah.
But if
It's AO, right? So that is known.
if you have, for instance, all non-crossing partitions, that's AO, that's known. Yeah. So but we can do it whenever we have only non-crossing partitions. There we can write it down explicitly. But if we have some more complicated categories involving crossings, then we can write down in a nice form some rough fusion rules. But the finer ones, we can also say something about this, but it's not very explicit. Yeah. Okay. Is there a question to this approach? I mean, this is really the link between the category of partitions and Tanaka-Krein, how to get a quantum group. Okay.
But you define ON plus and things like that without
Right.
and that will what will correspond to the full partitions and what will correspond to non-crossing partitions.
We will see in a minute. So this is now the next thing that I'm saying, because this is the approach to easy quantum groups, and we say that a quantum group is easy if it is constructed in this way. Okay. And I will now tell you why ON plus and SN plus, why they are easy. so now comes the definition of Barnecker and Speicher from 2009. A compact matrix quantum group is easy if it is obtained this way. I will give another characterization in a minute, but this is the way I motivated it now. This is a good definition, and hence A is the universal C-star algebra generated by elements Uij, which are self-adjoint, and the relations Tp U tensor K equals U tensor L. Tp for P is in CKL. Okay, so here from this A and B, we see that it's the universal C-star algebra, and that these relations are the defining ones. Okay, so let me now check explicitly what does this mean? What does such an equation mean? Okay, so what is it? So this is, so we have so what is U tensor K? This can be written as E alpha 1 beta 1 tensor E alpha K beta K tensor U alpha 1 beta 1 product U alpha K beta K. Okay, so this is the definition for the tensor product, and we may let it act. In the following sense, namely we can say something like this. This is given as E alpha 1 tensor E alpha K tensor U alpha 1 I1 U alpha K IK. Okay, so this is in MNC tensor MNC tensor the C-star algebra A, and I can let it act on these basis vectors just by saying, okay, so this is a matrix coefficient, and which matrix coefficient is it? Well, it's this one, right? So this is how U tensor K acts on such vectors. And now I can also let act Tp on such vectors, and I can just write down what this equation means. So thus I have Tp U tensor K Ei1 Eik tensor 1. This equals, I first apply Uk. So it looks like this. And now I apply Tp. Looks like that. And then I have the sum of the g's. Okay, so this would be my calculation here. And now I do the same with U tensor LTP. And if I do it, I will obtain this sum of this form. Okay, so I'm just calculating these two things, and now they should be equal. So comparison of coefficients tells me that this sum should be the same as this sum. Okay, so this is my relations that I will obtain in the end. So they are the same. Like this, whatever. Okay, so you see that these relations here, these were these complicated intertwiner relations. Okay, so we had those they come from the monoidal category. Then we had these morphisms. We had these intertwining relations. But this really translates to some relations on my Uij. So now I'm in the C-star business. I have relations. I know what to do. There's no intertwiners and anything involved. It's just these relations. Okay, so this is very easy. So let us now check. Okay, so maybe I should say this. If now my k is 0, then I don't have a sum. I just have the delta p 0j. Okay, so if k equals 0, then I have just this. And likewise if L equals 0. Okay, so I allow the case k equals 0. So then I don't have a sum here. I only have the delta p 0, s, and I don't have anything here. Okay. In this sense, we have that P corresponds to Sn, and all non-crossings correspond to Sn plus, whereas all pair partitions correspond to On, and all non-crossing pair partitions correspond to On plus. Okay, so I will say in a second. I will say what this means. But here you see these are explicit relations. So I will now write down the relations for this NC, and we see it's exactly the relations for Sn plus. Hence it is easy. Okay. So before proving this, when you look at this, this has a very nice aesthetics, right? Here I have a group. Here I have this free quantum group. And what do? I take the partitions and I restrict to the non-crossing ones. Here I have a group and a quantum group. I take the partitions and I restrict to the non-crossing ones. So this is something. If you do free probability theory, then there rings a bell, because in free probability, all partitions as classical world, non-crossing partitions as free world, and the same is true here in this quantum business. If you don't know about free probability, never mind. But then you see that apparently this structure that you don't have crossings, this has got something to do with this adjective that I always said. It's free permutation quantum group, free orthogonal quantum group. Okay, and there are other examples with the free and this. They have this non-crossing partitions there. This P2, these are all pair partitions. So all pair partitions, these blocks have size 2.
So in both cases you're restricting from P to something, and you're getting the map from the other direction, right? Sn plus to Sn. So is it a functor, right?
Yes.
Restriction.
Yeah, it's a functor, and this comes out from this universality in Voronovich's theorem. If you have one monoidal category and you have a bigger one, then you have the same for these quantum groups associated to it. I mean, the arrows turn round. Yeah. Okay, so let me maybe check this partition. What does it yield? Well, let's check what's happening here. Okay, so now I have 0 upper points and I have 2 lower points. So on the left-hand side, I have delta P0, and now this S is a multi-index of length L, which is 2. So it's like that. And this is, on the other hand, it's from J1 up to JL. My L is 2, so J1, J2. Delta P, my I is a multi-index of length K, which is 0. And then the J. And now I have U S1, J1, U S2, J2. And what does it mean? Well, I have 0 upper points, and J1 and J2, they are my lower indices. So this was, I have J1 and J2. I have my partition P, and it only connects equal indices to equal indices, which means J1 must be equal to J2. So I have this, and likewise here I just have delta that S1 equals S2. Okay, and this is exactly the relations which make U transpose equal to 1. Okay, so here this relation means I take this matrix here, so I have, so what is the S1's S2's coefficient of this matrix? Well, you take U S1 J1, and then here from this one the coefficient, since it's a transpose, it turns round. So you have this is the matrix multiplication here, and it should be delta S1 S2, which is exactly what I have here. Okay, so this is really just orthogonality relation. And likewise, this is this. Maybe let me check one more partition. This one, what does it mean? Well, it says delta P equals 0, S1. I only have one index, and it's the sum over the J1, delta P0 J1. I mean, now my K is 0 and my L is 1, so it's like in the case above. I just have this. But this is, of course, this is always true. So S1 must be connected to equal indices, so just to itself. So this is 1. And this is also 1. So if I want to write it in a different style, I can write it like this. Okay? And recall that this was one of our relations of Sn plus, right? Okay. So for the other partition, which just consists of one upper point, I get this relation. And as for this partition, I will get Uik Ujk equals 0 equals Uki Ukj if I is not the same as j. And also, you can just check that if you take this crossing partition, you will get that the Uij's commute. Okay, just by checking the relations, you will see that this means that those commute. Okay, so this is, whenever you have this crossing involved, then you get that the Uij's commute, then you're in the group case. Okay.
So you have to do the other way also, right? From these relations, you can recover the other relations too.
From these relations,
You have written down all the relations for Sn.
yes,
But the relations for Sn should satisfy these relations.
that's true. Yes, yes. Yeah. So I mean, by this, by this we see that hence associated. Okay, let's say G prime. Hence, if G prime is associated to to NC, then we have that CSN plus, maybe if this is A prime U prime or something like this, we have such a map. Because here in this A prime, all the relations for all non-crossing partitions are fulfilled, in particular those. And if you just take those relations, you see that those relations of Sn plus, they are fulfilled. Okay. So this means you have a morphism from here to here, and you can check that in Sn plus all relations corresponding to non-crossings are fulfilled. Are fulfilled, so hence we also have the other arrow. And they are the same. This is what you meant, right? So you take these particular partitions, you take the associated relations, and they imply the relations of Sn plus, so I get this by the universal property, but conversely, in Sn plus, not only these relations are fulfilled, but all for all NC, so I get the other arrow. And if I now take all partitions, then in particular this one is fulfilled, in particular the Uij's commute, so I will get Sn, and yeah, conversely. And you can also check this for On plus. Okay, is there a question? Okay, so now, since we have that for every category of partitions is contained in P. Okay, so that's by definition, but it also contains this non-crossing pair partition. So I will say something about this in a second. So since this is true for all categories, we have Sn is contained in G is contained in On plus for all easy quantum groups. Okay, so if I take any category, this gives me an easy quantum group. Now this is contained in P, which means that in here, associated to this category in this quantum group, all relations from here are fulfilled. So I get a morphism from G to Sn to Sn, and this means that Sn is a subgroup of G. So it does this. So this is this functoriality. Okay, so again, here this category is contained in P, which means that in here all relations related to P are fulfilled. In particular, those related to the category are fulfilled, which means that by the universal property, since this is a universal object, this surjects to here. And likewise with this NC2, this corresponds to On plus, so this surjects to this one, and this is just recall our definition for quantum subgroups. This just means that if you have such a surjection, this means that Sn is a subgroup of G. And this way there's another definition. And this is the original one. Yes.
Why is that?
So I will prove this in a second. So I will explain this in a second. So the other definition of Banneker and Speicher is a compact matrix quantum group G with Sn contained in G contained in On plus. So this is easy. If there's a category of partitions such that the home space, which is just the space of maps T such that T tensor U T apply to U K UL equals T, so the space of intertwiners, that this is span of TP for P in CKL. And it's free if C is a non-crossing partition. Okay, so this is just a reformulation of what I did. I defined easy, saying I start with the category and I associate a quantum group, and if it arises this way, then it's an easy quantum group. But this is, in fact, since we've seen by this universality of Voronowicz theorem that they are determined by these spaces, we can say a quantum group sitting between Sn and On plus is easy if there's a category of partitions such that this intertwiner space is spanned by the maps TP.
And what does it is free mean?
We say it's a free easy quantum group. There's a definition if the category is contained in the non-crossing partitions.
No, the last statement is a definition.
There's a definition. Yeah. It's called free easy quantum group if this is the case.
For any compact matrix quantum group,
Mm-hmm.
any irreducible representation will occur as a sub-representation of U power tensor K. Is it true that you can recover?
Yeah, so if you have any compact matrix quantum group, say if you have this, then the irreducibles, they are always contained in some tensor powers of this form, and otherwise you have to take such tensor products.
Okay, U tensor. Okay.
Yeah. Okay, so this means thus we have that categories of partitions, they are in one-to-one correspondence with easy quantum groups. Okay, so this is the game, and this is exactly what makes easy quantum groups interesting. Here you have the operator algebraic object, you have a quantum group, whereas here you have a combinatorial object. Okay, and you have this one-to-one correspondence, and now you can start to make a list of properties. So say you have a property here. What is the property here? Yeah. So for instance, the representation theory, so the full representation theory, the fusion rules, and so on. You have it here on this side. What does it correspond to on this side, and other things? So you can just start investigating it, and this is what we do. Okay. So let me now come to the next chapter. Okay. Yeah. So okay. No. Maybe first I just orally I will maybe elaborate a bit more on this bijection. So why is this interesting? So first, one could try to understand all compact matrix quantum groups by understanding the easy quantum groups first and then transfer it maybe to the other compact matrix quantum groups. So something like you have some behaviors for compact matrix quantum groups, then you study this for the easy quantum groups first, you do this on the combinatorial level, and maybe you get some insight just by the combinatorial level. Okay, so the philosophy for the easy quantum groups is all operator algebraic properties should be hidden here, and so together with my co-workers, I tried to find explicit examples for this philosophy, and we have two papers on this, where there's some property here which we can express in combinatorial terms. So I will speak about this next week.
Approximation property?
Yeah, so I mean, first we did it for the fusion rules, and from the fusion rules you can deduce some approximation properties, for instance, yes. Yeah, or we have something else, but I will explain this next week. And yeah, so as I said, also this somehow you can think of maybe taking subgroups of ON plus, which also contain this Sn. Maybe they can be pretty complicated, and somehow the easy quantum groups are maybe they are a backbone in this theory, which is a bit more approachable.
But it's not true that any quantum group which lies between ON plus and Sn is an easy one, right?
Yeah, that's not true. Yeah. So with Sven we have an abstract result that there's a non-easy quantum group sitting here, but so far we are lacking of examples of concrete non-easy quantum groups. Yeah. So really to write it down explicitly. And there are some paths where it's not known. So for instance, you could ask so Sn sits inside Sn plus, sits inside On plus, this one sits inside On plus. And for instance, here we know that there's no easy quantum group here, but we don't know is there any quantum group in between these two. We don't know. On this side, we know that there's one in between, an easy quantum group, but we don't know are there others which are non in between. So there's a smaller part where we know that there's no quantum group at all in between, but yeah, things like this, there are many open questions. Yeah.
Why is that fusion groups are always commutative here?
Well, I guess for Hn plus they are not, right? For Hn, there's one quantum group where they are not commutative, or how?
No, it lies between Sn and so it has to be commutative. What is fusion?
Between Sn and On plus. So you want to see this on the combinatorial level?
Yeah, exactly. I mean, On plus is definitely commutative.
Yes.
And it is a subgroup of G, right? I mean, so G is a subgroup of 1 plus, so it must be also a commutative fusion group.
Okay, I'm not so sure if I. So there's one quantum group which is called Hn plus, and there the fusion rules are a bit more complicated, but it might be true that in the end they are commutative. So I should check that. Yeah. But we will speak about the fusion rules next week. So until then, I will have it checked. Yeah. Okay. So this was one story within the quantum groups why this could be interesting to have such a link. The second thing is, when you know free probability theory, as I said, this really looks like something in free probability theory, and in fact, for free probability theory, for some things, the easy quantum groups are the right symmetries to describe certain phenomena. Okay, so you have certain phenomena in classical probability, which you describe via groups, and for this free probability theory, you describe it via easy quantum groups. Okay, so in the very beginning, I said groups are something like symmetries. You take a space, you ask for the symmetries, and in some sense, we have explicit examples where this is the right symmetries in the non-commutative world. Okay, so this is another use of these easy quantum groups. And the third thing is that once you have a quantum group, you have a Haar state. You can associate a von Neumann algebra, and now you can investigate this von Neumann algebra. So this is a way to get many examples of von Neumann algebras. And in fact, the von Neumann algebra associated to ON plus very much looks like the free group factor. And people would be interested in knowing, is it really isomorphic to the free group factors? Is it non-isomorphic? Maybe we can reflect the isomorphism problem for the free group factors in terms of quantum groups. Okay, so of course this is all very vague, but this is what some people are interested in, studying the von Neumann algebras associated to it. Okay, so these are the three aspects why people would like to know more about easy quantum groups. Okay, but all of this we will do next week. Let me now say that once we accept that easy quantum groups are interesting, we might want to know, okay, so how many examples are there? So tell me more. Give me more examples of easy quantum groups. Give me more examples of quantum groups. So let us study categories of partitions, and this is the classification program of categories of partitions. This has recently completed by myself and co-workers. So right now we are able to give a full list of all categories of partitions. Okay, so the full list of all easy quantum groups, and maybe this helps for the other questions too. So I will tell you a little bit about this now.
Is that selection finite?
Sorry?
Is that selection finite?
No, it's even uncountable.
Category partition.
Yes, yeah. So if you restrict to these free ones, then there are only 7. If you restrict to those that are actually groups, then there are only 6. But there's something in between, and there's a huge number. And the complexity, in fact, is very wild. So when I say we can give a full list, I'm cheating, because then we transfer the problem to a problem in group theory, and if the group theorists are able to give a full list of these groups, then we're done. But, yeah. So I will tell something about this now in this next chapter. Classification of easy quantum groups. So my first lemma is, so today I will play around a little bit with the properties of categories, and next time we will complete the classification. So any category of partitions is closed under rotation. What does this mean? This means if you take a partition with k upper points and L lower points, and if this is in C, then also the partition obtained from shifting the very left upper point to the left of all lower points. And vice versa, and also on the right-hand side. So how does this look like? For instance, if we take this partition, so 4 upper points, 1 lower point, I can now shift this point to the lower points, which gives me a partition of this form. Okay? So this partition is also in C. So if this is in C, then also this is in my category. And I can also maybe shift this point to below. Yeah, okay, I take this right point, shift it to the lower line. I can also shift all the points down if I want, and I can also start shifting the points up if I want. Okay, so this is the rotation.
You have two specific partitions which you demand to be in the category, right?
For this one?
No, no.
Ah, yeah, yes, exactly, yes.
One and what is the second one?
The identity.
So one of them is
One upper, one lower. So these two. And they are exactly used now. So I will prove it. So what you do is you compose in the following way. You have these K upper points. You have some L lower points, and you have your partition P. Okay? And now what I'm doing is I can compose this partition P with this identity partition, and of course this is still in my category. So this identity partition is in my category, P is in my category. I say the category is closed under tensor product. Okay? So this is in my category. Also this pair partition is in my category. So this means this partition is in my category, and also if I compose it with a lot of identity, if I take the tensor product with a lot of identity partitions. Okay? So this partition here is also in my category. And now the composition of the partitions is again in my category. So this, what comes out, is also in my category. And what does it do? Well, I take upper points, these points are left invariant, so P does anything with them, but this point here, you see, it's shifted to below. Okay, so this is exactly this rotation. The point which was before here is now below. Okay, so this is the rotation. And this way we can now prove that NC2 is in C. Lemma. So by this expression, the span of P1 up to Pn, or the category generated by it, we denote the smallest category which contains P1 to Pn. Okay, I take a few partitions and I say this is the smallest category that contains these elements. In other words, this category is generated by these partitions together with the category operations. And we have that NC2 is generated out of nothing. So by this, note that we always have that these two partitions are in a category, and we omit to write them down. So if here I mean only partitions which are not these two. So if I write it like this, I mean I only use these partitions and the category operations. So tensor products, composition, involution, and also rotation, since I know that it's also invariant under rotation. So we have this. All pair partitions are generated by this one. All non-crossing ones by this. And all partitions are generated by this. Okay, so once I've proved this, then of course NC2 is contained in every category, right? Okay, how comes? So maybe let us first okay, let me first explain something about non-crossing partitions. So let P be a non-crossing partition. So since P is non-crossing, there is at least one block only consisting of consecutive points.
What do you mean by this arrow?
This one, I guess I had a definition before. I mean this one. Just one point, one lower point.
Top there is nothing.
Yeah, so I don't know why they like this notation, but I think if you just would write it like this, then it would be too close to the identity partition. Okay, so it would be hard to distinguish these two things. And if you just write a dot, then maybe it's also inconvenient at some places. So this is just a symbol for saying it only consists of one lower point. Okay, so now if you take a non-crossing partitions with no upper points and only lower points, how does it look like? Well, it will always look like maybe something like this. So I start with 2 points and it's like that. And then I have another one here. Okay, so non-crossing partitions will always look like this. I have only lower points. I can connect them by some lines, but they are not allowed to cross. So they will always look like this. And of course, since this is non-crossing, there must be at least at some point, there must be a block which only consists of consecutive points. Okay, because if you take 2 points and if all points in between belong to the same block, then you found one. Otherwise, there must be a smaller one inside. And you do the same with this one, right? And iteratively, you see that this is always true. And if you now remove this, then again, you get a non-crossing partition. You can again do this procedure. And in the end, you will only get a partition which consists of one block. So this is an inductive way of getting all non-crossing partitions.
What do you mean removing? It's
I just take it out.
by composing it what?
No, just taking the same partition and just leaving it away. So it's not within the category operations. I just mean that the partition when I erase these points. So if this is my P, so my P would be the same without this one. I do not use any of the category operations for this.
But you want to show that P is generated by those two things, right?
Yes. But for the moment, I just say that this is a
This is first of all there.
yes. So this is a inductively we obtain a one block partition. So this is an inductive characterization of non-crossing partitions. Okay, so let me now take let me now prove this here. So now, of course, we have that this one is in NC2. So I'm just saying, okay, so this is a trivial statement, okay? So here I say I take the smallest category, which is just generated by the pair partition and the identity partition. And of course, the pair partition and the identity partition, they are always in any category. I check that this is a category of partitions, so I have this relationship, okay? So now let me prove the converse. I first just take a partition which only consists of lower points. So now, removing one of the blocks like this of consecutive points. We obtain another partition which is also non-crossing pair partition. Okay, so if I take such a partition, it's a non-crossing partition. So by this inductive characterization, there must be one block consisting of two consecutive points. And since I only have pair partitions, it must be of this form. Okay, I take it out, and my characterization tells me I still have a non-crossing partition, and of course still all blocks have size 2. And now inductively I can prove that this one is in here. Okay, and by induction hypothesis, so we have that P prime is in here. Okay, so I do this inductively, and composing it, with this partition yields that P is also in this category. Okay, this partition here for suitable alpha and beta I do not specify. This is always in my category, and if I now take my P prime and I compose it with this one, then I will get my P. Right? Because if I okay, so this is not a good example because this is not a pair, not a non-crossing pair partition. Let me say it looks like this. So now it's a non-crossing pair partition. At some point I remove this one, I get my P prime. But if I compose this P prime with this partition, I will get exactly back the partition that I had before. Okay? So this is the proof for this one here. Okay.
This also tells you that non-crossing is generated by those two things, right? You just
This one, you mean?
yeah.
I need a bit more, right? I will do it now. So here, of course, this is clear. This is a non-crossing partition. This is a non-crossing partition. They are both contained in here. This is the category, the smallest category containing these. So the whole category must be contained in NC. Okay.
By that picture you mean the one with exactly 0 and 4, is it?
This one. Yes. Yes. No upper points and the 4 lower points are all connected. So I have this one direction, I have to prove the other direction. Let P be in NC. Maybe for simplicity again, let us only take partitions without upper points. I mean, I left out this argument, but if you have partitions with upper points, then you can rotate all lower points to below. Then you only have partitions of this form. If this is in my category, I can rotate the points back and then I get my partition. Okay, so since I have this rotation, I can always assume that I have no upper points. Okay, so let P be such a okay, maybe before let us say something else. Namely, since this is in my category, we also have that this partition is in my category. Okay, I take this 4-block partition tensor product 4-block partition. This is in my category since it's closed under tensor product. Identity, identity, identity. This is the involution of the pair partition. Involution was just turning upside down, so this is also in my category. Tensor, identity, identity, identity. So this is also in my category. Composition 2. And what does it mean? Okay, it means I have 6 points which are all connected. Okay, so by this I get inductively I see that whenever I take a block where 2 endpoints are connected, they will always be in my category. But now, if I take the one with 2n minus 1, this is exactly the partition where I take 2 endpoints and I compose it with this partition and the involution of this guy. So the involution of this guy is, of course, 1 upper point, 0 lower points. Okay, it's just turning it upside down. If I compose it with this one, I get 2n minus 1 points. Okay, so I get all blocks of all sizes. So all 1 block partitions of all sizes are in this category. But now if I compose them correctly, I get all non-crossing partitions just by this inductive procedure here. If I take a non-crossing partition, at least 1 block must be of this form. I take it away. By induction hypothesis, it's in my category. And if I compose it, I'm allowed to use any of these blocks, and then I get back my partition. Okay. So by rotation, I get all of these inside my category. Okay, so this is the proof for this one. Is this okay, or is there a question? You have to play around a lot with these category operations, but it's if you take your time and just think about the steps I did, it's really trivial. Okay, and using this one, we have all transpositions in a category. So if this is in a category, we have all transpositions in a category. So we can always flip to neighboring points. So we may permute points arbitrarily. And this proves these are the 2 statements. Okay, so take any partition. Using this one, you may just permute it such that it is a non-crossing partition. Then it's in here, and then you permute it back, and then you get the partition back. Okay. So this really gives us a very easy way of describing these categories, and of course by this we immediately get two new examples.
So does this mean that in that the relations are given by these simple diagrams?
Yes.
It does not need to be satisfied for every but only for this kind of partition.
Yes. Yes, that's exactly true. Yeah. So when we had this proving that this corresponds to Sn plus, recall that I only checked this one, and this one, and they are basically these partitions. So
It's enough. I mean, what I mean saying is that it's enough to check for generating set of
yes.
partitions.
Yeah, I mean you have to be a bit careful because if you only take these partitions, for instance, it's not so easy to see immediately that this is Sn plus. But so sometimes you should also take these two. But in general, that's true. Yeah, I mean this is also non-trivial, but in general you only need the generating set. Yes.
So what will be X and one arrow?
What do you mean, this one? What will be the category?
No, why
What
this
will
is
be the category
generated by this?
What this is, you mean? Yeah. Okay. So of course you have. No wait. This way. Okay. So this is in here. This is in here. So also the tensor product, which is exactly this.
So X comma. When you are looking.
This one. Okay. Yeah. This is also a new example. Yeah. So this is the group which is called.
Not equals to,
Sorry.
this is not equals to P. Means I wanted to see that P is generated. You mean 3 partitions.
Yes.
Elementary partitions. Say.
Mhm.
But is it means only these two can generate P? Is it equals to P? That is your question.
No,
To P?
it's
No, no.
different category.
It's another category, yeah. So it's not the same as this one. It's another category, because here you only have partitions with blocks of size 2 and 1. You cannot produce this one.
So what is the similarity if you drop the middle one out of P?
This one,
So if you drop the middle of the
Secondary.
yeah.
this one. So this will be Hn, which is exactly this strange breath product that we had in the very first lecture. So that's this one. And this one is the group Bn, which is called the B stochastic group. Yeah, but this really gives you immediately a way of producing examples, because if you forget about this crossing partition, you can also take a look at these partitions, for instance. Okay, so now we have, this is a non-crossing partition category, this is a non-crossing category, non-crossing category, non-crossing category, and this is a quantum version of this group, and this is the quantum version of this group, so of this group. Okay, so this is a quantum version of this group. Next time I will write down these examples explicitly, but probably you see that you immediately can play around, right? You just choose arbitrary partitions and check what's the category generated by it. Next time I will tell you that if you want to do it in a non-crossing way, so subcategories of this one, there are only 7 possibilities. And then I will tell you how to deduce all the other examples. Okay, that's for today. Thanks.